for once the same thing. I've been spending two years on this, and I finally think that I know what's going on. The literature is very it is not as good as you might want it to be. So I think we have missed the so let me turn off the lights. So some terminology. We have forecasting and nowcasting. So a forecasting approach is you say the weather is like this today, and you say what will it be tomorrow. That is the hardest problem. But there is even which is still a difficult problem, and that is what is the weather now. How can you get into what's happening there into your computer? And that is not a trivial problem because you have scarce observations, and how do you express this thing in terms of something that your computer actually reads on? So for the forecasting, we have the initial value problem. And for the initial value problem, you of course need an evolution model. It could be the pencil code. It could be a weather simulation. It is something that takes the initial state and propagates it into the future, and then you need an estimate of what is the current state. So the problem when we are looking at nonlinear systems is that we have sensitivity to initial conditions, and this, of course, this notion is something that we are going to know that the precision of the current state makes it very hard to predict into the future. But there is another quite disturbing fact proven by Judd and Smith, that the sensitivity to initial condition also shows that it is impossible to find the current state. And that is because you can always find, if you have noisy observations, states which is indistinguishable from the true state. So it's actually impossible to find the true one, because you can always find close ones which is indistinguishable. That means that you can say which one is which. I'm trying to use this. So what is this about? So here we have, and this of course don't support supports. So we should look at the things on the left. So this is a convection simulation with mixing length theory. Look at these two, and it is the velocity field as a function of time. And these two are identical. The only difference is the random seed. So after time, they're typically not similar. They go apart. And here we have a graph of the midpoint, the velocity field in the midpoint. This is all horizontal velocity, and we see that the dashed line is the reference one, and this is the second one, and they grow apart as a function of time. So what to do about that? The interesting thing is, so one can of course make constant corrections to this.
So yes, okay.
So here we see the true one. Up there we see the corrected one, and the corrected one started like this one, but every 10th time step we make a correction.
How much is that in terms of kilograms, or what is the RMS velocity? And the yes, what is that? It's 0.1, right? And the length of the time step is 10 to the minus 2 or what?
I think it is the gene. I don't know. That is the crude answer.
There's probably roughly 1 turnover time after which you're correcting, I think.
Yeah. So.
What do you mean by correcting?
Huh?
What do you mean by correcting? And what exactly are you doing?
So that is what I will be talking about. What I practically do is I read the current state, I calculate a correction, I write a correction map, and then I go forward. So what is this medical correction?
Correction to mean velocity field or correction to instantaneous.
To the whole velocity field. I basically explicitly change the velocity field.
To set new initial conditions or something.
Yes.
So you are synchronizing somehow the
So, some kind of review.
Yes. Now I have to see if I can get back to my. Okay. Yes.
If you have those fluctuations, why you would work with the instantaneous velocity field, not with the mean velocity field?
So, because what you want to do, if you want to do a prediction, you want to know what is the velocity field. If you want to predict the velocity field in the future, you have to know the velocity.
Well, it depends on time scale you would like to. If you would like to predict long-term behavior, it's one
Possibilities,
Yeah, but that's like the difference between weather and climate, right?
yes.
And
But you know, nevertheless, in some sense, because if you speak about convection, solar convection, or weather, in Earth's case, you cannot use exact equation. You forced to use some kind of effective equation. So in some sense, it's average.
So at the moment he's considering the fluid equations. And at a Reynolds number, or Rayleigh number, which is for 10 to the 5th maybe or something, that's a very stated problem.
10 to the 5th, it's not
You're probably not doubting that the equations are correct. So we know what the equations are, and he is producing a virtual reality that he is trying to reproduce. And as you see from these two pictures, the virtual reality we started with a slight noise initially departs quickly from the actual virtual reality.
Yeah.
So there's no need for any other equations. Everything is well known now.
So this is what we have. We have a true run, and then we have a reference run, and they grow apart at a bunch of time. And this is the horizontal velocity field in the midpoint. So what do you do with this?
But you can define a Lyapunov exponent for this.
It has been done in the 90s. And typically the Lyapunov exponents are of the order of the growth rate of the instability of convection.
But a spectrum of Lyapunov exponents. You mean a spectrum of Lyapunov exponents?
Yeah, the fastest one is the upper bound to the growth rate, right?
Yes.
Okay. So we have a true run, which we say this is the true one, and then we compare it to another one called reference. And this is a so-called twin experiment, where you take a true known state, and then you do the whole machinery and see if you can get the same state back. Because if you start with observations, then you don't know what you get is close to the true state. So here we do the ideal case of we know what we started with and see if we can get it back. So we do this by adding random noise to it. This is so-called synthetic observations, and this is on the order of 20% of the amplitude of the box, which is very big actually. So in the real world, these observations is all you got, and you want to find the curve given the observations. So this is the observations next to the reference states, and you can say that that graph follows that in some way. You have an outlier. It's kind of hard to say which of these two is.
So the continuous line is your reference run?
Yeah, this is the reference run, and this is the true run.
No, the continuous line is the reference run.
Yeah,
And then you generate the synthetic observations by the...
from the true one. I take the true one and generate synthetic observations.
But this you
By just adding random numbers at some points, or...
So what I do is at every 10th step, I'm applying Gaussian random noise with a certain variance on every point, and say that is my noisy observation.
So it's kind of saying that after every one turn over time, and putting in some probe into the system and measuring it,
Yes.
and the probe has a certain error in it,
Yeah.
and that's the Gaussian random noise coming from.
Yes. Okay. So basically, it's kind of hard to say given the observation what is the right curve. But now we make a correction. So basically, we are running the pencil code. We are stopping the pencil code. We are making a correction here. And these corrections is of course not very nice. These spikes, I'll come back to the spikes, but in between the spikes, it follows the curve quite nice.
The corrections are at every point.
At every 10th point.
No, but
When you have a whole observation, you make a correction.
no, but I
In
mean
all possible points.
in space.
Yes.
And time.
no, only
Yes.
at each
Every
observation.
10th time.
Every step. Or every some special
Every 10th.
step.
Every 10th time. When you have a whole observation.
But the observations, of course, cover the velocity at each point in the volume. In reality, you may want to have some kind of a line of sight velocity only, or something like this, which can also be incorporated in the tool.
When they've got stations,
Yes.
lots of stations,
Yes.
a lot of points, and grid. For example, in small countries, Estonia, they've got huge numbers.
Yeah, right. But then you have the oceans, and there you don't have any points.
No, they've got Baltic cities. They've
And of course, you need to take that into account if you don't have enough points.
not if you speak about Sweden or Baltic countries, not important, but for England, for example, it's important. For England, for US.
So you have in this case you have just some run
Yeah.
with the initial conditions are close to what you think the true run is.
Yeah.
And this run will evolve and will by itself diverge from the true run.
Yeah.
But every time you have an observation,
Yeah.
you correct this run according to some recipe.
Yeah. And then you continue from the correction. So here we have the difference between the true run in black and the corrected one. And of course the spikes is very unsatisfactory, and then we have a small deviation here. But basically it captures the behavior quite well. And if we compare to the reference run in green, it's clear that it captures the true one and not the reference one.
So even if the correction are done with points that have noise with respect to the true one,
Yeah.
still the corrected solution is closer to the true one than the uncorrected one.
Yes. Which I will come back to, which is it's surprising that with these big spikes, it is still so good.
So if you kind of, other than taking it at every 10th iteration,
Yeah.
if you take it as every 20th radian,
Yeah.
it gets worse.
So you have there is one parameter to play with, and the other two is basically how much you are weighting the observations or the simulations, and these three parameters can be explored and see that if you have longer assimilation windows, you need a better observational loss for them. And this is just an example, but it seemed to be surprisingly robust. So this is for 64 squared. This is for 16 squared. And here we see the true one in black. We see the reference one in green. And we see the corrected one in yellow. And here it's very bad. But it starts to catch up. And here it's actually quite good. So this is for 16 squared. It's more wobbly when you start to...
For 16 squared, the length of the time step is 4 times longer. And if you still use every 10th time, then you have, of course, a correction time which is 4 times longer than before.
Yes.
That's probably the reason why it's overall not so good as in the...
Yeah,
other one.
that makes sense. But still, you see that it kind of catches up here and follows quite well. So. And for the 32, we see the green one goes crazy and it goes away, and the yellow one follows the black one. Very okay.
So correction means to mix the simulated state with the observed state.
Yes.
You mentioned weights which are used there.
Yes.
Is the weighted evaluation
I will
a mix?
get to exactly the performance. So, and here is back to the 64 schools, where it's quite nice. So, practically, how is this run? You are, this is the 3UR, which I'm using, which is intermittent assimilation scheme, which is you're running your code here. You have a background state, XB, and then you have observation here somewhere, and you make a correction, and then you continue to run. So basically you are running, making a correction, and keep running. The other alternative is that you do a time series, and then you vary the initial condition here, and find the initial condition that gives the best overall fit. Yes?
As I know, in meteorology, they use a little bit another scheme. They work, for example, for point A,
Yeah.
correction. And what they do, they start not from point A, they start before. Say, I don't remember, maybe 1 hour before something. They make correction each 6 hours. In order and find initial condition, try to find initial condition which goes to A.
Yeah.
That's kind of what you do.
Yeah, in the second case, right?
So they don't start immediately from this point, they start before,
Yeah.
in order to arrive more smoothly.
Which is the second case.
Second,
41. Which I'm not implemented because it's much more, because then you have to run the pencil code a lot of times instead of running the pencil code, stop it and run it. So it's much computationally cheaper. So how is this practically done? This is the cost function which encompasses everything. And what you practically do is you are minimizing this cost function given x. You want to find x that minimizes this cost function. And where it comes from, I will get back to you in the derivation. So basically what we see, it has three terms. Of course, the constants can be ignored because we want to find the minimum. And then we have the first one, which is about the simulation, the background state. And then we have the observations. And then we have these two, the B and the R, And
What
they are,
observation? Excuse me, what the observation? B, it's B is observation.
this is the observation,
Uh-huh.
y0.
Mhm.
This is the state of the simulation before you make a correction. This is a thing that translates between the variables in the model to observables. So basically, it's projections from variables to observables, because you have to have the right dimension. This is the variance of the simulation, and this is the variance of the observations. So basically, yes.
Go ahead.
So basically, if we have a very small variance of the simulation, if we think that the observation is really good, then for if we think the observation is very small, then the contribution, then this is the inverse, which becomes a big number, and this ratio has to be close, and our x becomes close to the state of the observations. And basically here, if the variance here is small, this thing has to be small. So basically, given these two, it forces us to be close to the observations or to the simulation.
So you are weighting them based on the variance.
Yes.
But the
And
variance of the simulation, how is measured?
so what you really should do is you should include covariances between the variables. So what you should do is you basically run the code for let's say 100 time steps, and then you do a lot of realizations, and then you do error statistics of what points typically are correlated, and that goes into the R&D.
So basically, that what you say is that I have my convection from simulation.
Yeah.
I run 100 realizations with different initial scenes.
Yes.
And I see how they diverge from each other. And that gives me an idea of what is the covariance at every point in time
Yes.
of that set of simulation, given that starting with different initial scenes they diverge.
Yes.
So that's again something it might be related to the Riemann exponent or something like that.
Yes. But it's more hard-coded brute force way of writing, and in a way I think it's quite neat because it's usually say that close by points spatially are usually at close by values, which means that if you have a more scarce observations, if you have a covariance here, you can't, because otherwise you would get, if you have a surface, you would get the spikes where you have observations. But if you include the covariance, we know that this point is typically correlated with this point, and that basically smooths out the solution, and you avoid these spikes, which I think is very nice. Yes.
In your case, H is just unity.
Yes. And age is probably the most scary thing because it's involved interpolation. It involves a lot of stuff, and that thing is typically non-linear, and this whole scheme has issues with non-linearities, which we.
But the dimension of y should be, in some sense, less than the dimension of x.
Yes.
And h is supposed to project it.
Yes.
But in your case, they are the same actually.
Yes, which is not a problem.
So I would expect that you would actually have what's matching than one would expect. I mean, I think if you, I mean, just speculating, say you have.
Usually you would expect the opposite, right?
No.
Because you have information on each point.
Yes, but you should not try to, I mean, this kind of comes back to what Nathan and Nicola were saying. You shouldn't try to match it at every point. I mean, maybe, because when you put a probe and measure it, you are not measuring it at every point. You are getting a kind of a coarse grain value. So maybe you should compare the 64 cube base with a 16 cube, where you have done an averaging over.
No, but why the probe is a point base, it's not a coarse base. When I put a thermometer out, I measure the temperature at the thermometer. I don't measure the temperature
Okay,
itself.
no, that's another kind of projection. Then see, then basically you need a filter which takes all your values and has a delta function at only at those points where you put your thermometer. It could be one of something, but something needs to project it from a higher dimension space to a lower dimension space. And the lower the dimension is, I think the better fit you will get. To lower dimension you project it to. Because you see, assume that you project it to just one zero dimension, so that you are looking at only the mean values. Then if you just want to match the mean URMS, then almost anything will do that. Your seed doesn't matter anymore, right? If you run two simulations with different seed, URMS generally matches.
Yeah, but that's not the same thing as the U at the center, right?
Exactly.
So what he wants to match is U at the center. It's not URMS.
Depends on the kind of projection you do.
Yes.
But it's kind of true to predict the mean temperature.
Exactly.
If the mean
So if
temperature is.
So if you make H project to a kind of very small dimensional space, then the problem becomes trivial.
Because you just get one curve.
Yes. If you do that, if you think that H is an operator, which just gives you the mean, then it's a very simple problem. Then it doesn't matter. But maybe then you don't want the mean, but something intermediate.
I think that you basically want Y to be as high dimensional as possible, because then you capture as much information as possible about the real estate.
That's probably one very valid way of looking at it. But another way could be that you are actually limited by what you have. I mean, Y is your observation and you are limited by what you have.
Yeah, sure.
So your age needs to actually fit to what you have.
Yeah.
So, just a minute. Matrix, B and R, in
Yes.
practice, hard to believe that something complicated. It should be very simple, go straight diagonal.
That depends. I will give you a picture of a covariance ring, and that is because the typical thing of you have, of course, points like this, and then you transform it into an array, and then you have points here and here, which is typically correlated, but they are not typically correlated here, which of course means that you have to capture that things close here are not close here.
But I mean, that would still be some band diagonal matrix. I mean, it's like doing a Poisson problem in.
I'm going to show you the matrix and ask you what you think I should do with it, because it's typically not trivial.
Another question, B is can be time dependent, right? I mean, that can depend on different epochs.
Yes.
So it will be different in the winter and the summer, for example, or will be different now in the middle of this week than it was on Sunday.
Yes. Or indeed can be functions of time, but typically they are. You
Don't do that, yeah.
You hope they are.
Yeah. Right.
But can they also be function of the initial condition? When you might have a system that you say, okay, I want to start from this initial data, and if I have the noise, the divergence is small, but if I start from a different initial condition and I have some noise, then the divergence is much larger.
No, I think it should be about the system, not the initial conditions. I think so. Yes. So let's get to the nitty-gritty here. So what do we mathematically want? We want to have the probability of, if you have given the observations, what is the true state? And we want to maximize our probability of finding the true state given the observations. And we know that we can express this as a likelihood, which is the negative logarithm of this, and this is basically J. So this is what we do. So we have a conditional probability here, which screams out, use Bayesian's theorem, which is this thing, which basically say that if you have a conditional probability like this, it is the same thing as this, and is proportional to this P, as we assume that the probability of this is greater than 0. So if you have 5 apples in your pocket and pick up, if we have 3 red apples and 2 blue apples, and then we pick up two random apples, and then we say we take these 2, and then we say what is the probability of picking a red one given that you have taken these 2. And that is basically expressed here, that you first do the probability of picking these 2, and then the probability of picking a red given that you're taking these 2. And this is that expression here. So this is back to what we wanted to solve. And if you apply the Bayesian theorem on this thing, you get this thing. And you can express it in terms of how these things are defined. That the probability of this thing becomes equal to this thing. It comes from definitions, and I can bore you with the details if you want. And we can assume that the probability, basically the noise around the noise is Gaussian, which is defined by this thing, and then we see that the B matrix comes up. And we can say that the observational noise has this R matrix, and the matrices is defined like this. The deviation minus the mean deviation, and then you have a matrix, and then you do the average thing, which is basically what I said, that you take out of realizations, you check the mean deviation and get the correlation, and then of course we have a P, and we said that we can define a likelihood J, which is the minus logarithm, which is nice because we have a.
Is it only mod B, not B squared, under the square root?
There should be square root. Square root is something.
Yeah, it should be like, it should not be here.
Yes, right.
It should be like that. That's correct. That equation was much smaller in the paper than in this piece. So, and that basically gives us the physics progression. If you just plug what you have, if you plug PB and P, you see that these terms here comes out as expressions when you do this J. And you get your nice expression, as we just said, that the likelihood J is equal to this expression, and then you minimizes this, and that gives you the maximum probability. So let's go to conclusion, and then we have some more points. So conclusion, it works. kind of the machinery of making corrections, saving, copying, writing to bar files without them crashing and so forth, it kind of works. And it seemed that the correction becomes closer and closer in time, as closer and closer in time to the true state, even for very large amplitude noise. It is although unclear whether this thing actually is better than just setting it to the value of the observations, which is not really satisfactory. It basically gives the same result if you just take and set xa equal to y0, which of course doesn't work if you have a coarser observation than the true value. And it seemed to have interesting chaotic properties. It seemed to have divergence of close by points, but it seemed to have an attracting subset. So it seemed to exhibit the two contradictory properties of a chaotic system with a large attracting set in high-dimensional state space, which actually was a big surprise. So, what to do? The covariance matrix and use that explicitly, and not just use the scalar variance, which I have using now to play around with effect. Do a more thorough aerostatistics, where correlation length is something that might come up, and this might actually be interesting to study aerostatistics of the simulation in themselves. Of course, we would like to have a 3D simulation, but then of course everything becomes bigger and you have bigger arrays, and especially the B matrix becomes really big because it's n squared, n by n, and if you have a 1,000 cube with 3 variables, it becomes insanely big. And of course, it would be cool to do real observations and use SOHO, for example. If you have a solar surface and then you take a square and you divide that and take observations, and then you impose those as observations and try and synchronize the pencil code. And when you think it's okay, you make a prediction into the future, and then you wait and see if your thing works. And of course, it would be nice to do a 4D bar, because then you never have these discontinuous jumps, which are not very nice to have, which is you have the corrections. So this was what I spoke about. Unfortunately, the color is not very good, but this is the difference between the 3D VAR and what you get if you just use the observations. And the only difference is like in the tips here. Otherwise, it's extremely close, and it was very hard to visualize. I think the only big difference is here, and there the difference is 0.01, and that could have to do with the definition of the variance, but something very strange is going on here. It should be better and make corrections that is somewhere in between, and not just.
I mean, you do have the noise, right?
Yeah.
Is the noise simply what the spike is? that it's, I mean, the noise comes, of course, in discrete intervals in your case.
Yeah.
Does that cause the spikes, in which case you would not have wanted to plot that actually?
So,
I think his complaint is that if he doesn't use the averaging at all, but just takes the observation as his initial condition, then he still gets very good data. So that basically means that almost running the code is almost superfluous. Is that?
running my minimization scheme doesn't really add much
Right.
from the current state.
But I think that
So
may
in
have
this
to,
case, you reset the observation
Yes.
without caring of minimizing it.
No, I am doing that, but the result is basically the same. The repeating bar tells us to basically use observations, but it will become a completely different thing when covariance is included, because then if we have coarser observations, that information is being distributed and propagated out.
I think it has to do with the fact that your observation and simulation have the same dimension. That's why you're getting it so good.
Yes, which is, of course, just as an intermediate step. It's just in the beginning
Yes,
of
of course.
things. The previous step was the Lorentz attractor, so this is then the next step. And then after that, the next step will be, of course, what you said, having a coarser one. And then after that, the next step will be to have just observations on the surface. Right.
So
in the model.
So this is not very fun.
So, but the question is, are you improving the quality of your run or not?
Certainly it's,
No, in the sense that if I stop doing this reset, let's say at time 100,
Yeah.
then the run will start drifting apart.
Yes.
And will they drift apart at the same speed as the original one? Or does this resetting procedure somehow make the original, make the noise smaller? I mean, do you approach the correct solution in a better way or not?
So I don't know, and that comes from kind of the machinery of the pencil coder on how to set things up, and that would be a very interesting thing of seeing. First of all, if you let free trajectory start before the correction and see how fast it goes away, and then make a one that starts here and see if it goes back, and if there you go, that's the win. Yes.
But if you don't make, if you don't improve your state by doing those corrections, I don't see the difference. If you just took, if you just started at every 10 time step the simulation completely from scratch, completely from zero.
So what?
It would be basically the same.
But the idea is, and that has
you have the
to be
knowledge.
checked, that
You can't do that, right?
Yes.
No, because if you say, okay, I will restart just at 100. Let's say there's a correction, and you say I will take as initial value the observation, right? But the observation of noise. So that initial state that you are taking is not a small perturbation on the true space. It's a 20% random noisy perturbation. So they're already far apart by 20%, and that will keep diverging. In this case, you are resetting to the, you are going back to actually your true state. It's not the same.
Yeah, but if you make an observation at time 100, which has a 20% error,
Yes.
then also your correction would have an error.
No, but if you look,
Yeah,
there is
if you have a good
20%
point.
mistakes, but you go back to the true solution in that procedure.
you have a good point, that actually in this case, when 3D bar doesn't perform better than the observations, which actually means that the background say, doesn't contribute much. But
But it never happened.
huh?
You don't see any jump in your simulation, right?
Yeah, you do.
But not away from the true solution. I mean, you see the spikes, but it go back again.
Yeah.
So it doesn't just spike and then drift from there.
No. Which is actually quite interesting that it's so. So, as we are speaking about that, this thing is huge. This I made another run with double the noise. This is a huge spike, and still it goes back. So you have a minuscule initial condition here, and it goes away here. And here you do this huge perturbation.
But I mean, that is because of noise, is it not?
Yeah, sure.
Yeah.
But still, you are applying noise, and the system finds its ways back very quickly. It's kind of like if you have a tractor and kick it out, it goes back to the attractor. But my picture is that here it is still on the attractor, but it goes away on the attractor. It's kind of
Can you time to resolve this better? I mean, what's the time scale on which it should relax, of course, in an e to the minus something fashion? So what's the time scale here?
You can go completely in another direction.
Random noise has a very different
Yeah, but this
character
one
from
doesn't.
that of
Yes,
the
this one
nonlinear
doesn't.
system.
Sure.
And chaos is different from random noise. So that is not surprising.
No. It's actually very nice that the system say, oh, this is not physical. This state is physical, and then it corrects it down to it. Basically, it is the same thing as the notion of a attractor or attracting set. That is the sensible physical state, and if you read it, it goes back to it.
But I mean, the green curve is also a sensible physical state, right?
Yeah, but it's not right.
Yeah, but how does this? I mean, you have large spike, and that spike managed to get back on the managed to get back on the true state, the black line,
Yeah.
and it doesn't manage to make you never jump to the green, let's say.
Actually, see, on the huge spike to the next small spike, they're all together. There's a second spike that actually connects it. I mean, look at it. The big spike takes it away, and then from the big spike to the next small spike, all the three lines are kind of together. And then the green one starts going away. There's a second small spike that stabilizes it, and then another spike later that stabilizes it again.
But for example, after the first peak,
Yes.
there is a small yellow spike.
Yes.
So, and the systems after that spike, which is comparable to the difference between the black and the green curve,
Yes.
example, he managed to go back to the black,
Exactly.
but he could have, why didn't he jump to the green?
It could have completely gone
I mean, you
somewhere
have
else.
many different oriented clusters, you just
Because the picture I like to present here is that this spike here, in a way, that is a deviation from the attracting set. That is a way of saying basically if you are moving around on a potential surface and then you put it goes back down.
Yep, I mean,
yeah, but I mean, but
But
why not the green?
perfectly valid.
no, I mean,
Why not
there's
the
a,
green?
No, it's should be a definite attractor, I would say. It's
So-
like jumping to a different road, right?
So I think that the black and the green are both on the attractor, and this leaves the attractor, and then they go back to the attractor, and then they go
No,
away.
but I'm talking about after the first peak.
Here.
No. The first peak on the black curve. If you follow the black curve, there is
Here.
a bump. Yes, there is a spike after.
Here, this one.
Yes. Why does it jump back to the black and doesn't jump to the green? There.
So this
Quite
is
far away, right? Quite far away in phase space.
But I mean, it's not that.
Assume that the spike would be upwards.
Yes, it's assumed that the spike will be upwards.
And notice that these two might be close in the midpoint, but they could physically be very different. This is the midpoint, and then you have a huge array around it, and they could be different.
Okay, so in practice, you are the correction due to the observation should never exceed in phase space the difference between two attractor sets. Because if it exceeds that, you could jump on another attractor.
Yes.
But we don't know what the difference between 50 to 6 are anymore.
Yeah, but that's a constant that you have on your observation, on your correction. If you cannot guarantee that your correction is smaller than the distance between two attractors, then you cannot guarantee that you are going back to the same attractor you were before.
But I think the space, I think the state space is so ridiculously huge that distances is not really an issue. And that is basically a question of, so yes, the question goes back to, is the physics of the system stationary? Or can it go between different kind of phases? And like you said, that when it leaves the attractor, then maybe the B matrix changes. But if you assume that the B matrix is the same, you are basically saying that you are on the same attracting set.
I mean, I think it could be an issue that the noise is producing solutions that are really completely unphysical.
Yes.
And so, for example, they could violate, suppose you have a divergence-free fluid, then of course the noise would not care about that and would produce you a divergent fluid. For us, of course, we are having compressor equations, but still, the sound wave will be quickly emitted and the system will go back to the nearly inelastic previous state.
Yeah.
So I think it's much more likely that you hit one of these completely unphysical solutions rather than a physical one which would then be really on the screen thing.
But I think the system is, that is a kind of, we think that physics is stable. If you hit the system, it kind of goes back to where it were.
Yeah, but obviously, as Nicola was saying, the green line is also physics. The green line is also physics.
Yeah,
if you
sure.
actually put it there by hand,
Huh?
if you actually put it there by, not by noise,
Yeah.
but by your design,
Yeah.
then it of course wouldn't go away to the black line.
No, but the point is that how far they are in phase space.
Yeah,
If they
yeah.
are very distant in phase space, there is no chance you have
Of
noise.
course. Yes, absolutely.
But you can also
Probably not very
restrict,
much.
you can also restrict your minimization procedure by fulfilling that it's
Yeah.
curve-free, for example.
Yes, you can do that.
Are you doing this already?
No.
What is UXS? What is it? Is it
Uh,
a vertical component of velocity?
It is the horizontal
Okay, no,
velocity, the horizontal velocity limit.
And
And that is the parameter I am assimilating. Oh, I have missed the big thing. This is x by z to the simulation, and I am only assimilating the horizontal field.
in one point.
No, in all points.
So your H is not unity of class.
No, basically, I am correcting only the horizontal field, and then let that the
Right.
vertical
That's
field.
there actually.
No,
That's
but
there.
H is unity.
No,
Yes.
no. You see, your state variable includes both the components of the vector. And he's assimilating only one component of vector.
but it's only resetting that. So X is only 2X, and H is
So
your
if
element.
is projecting the, so observation is, say, if you have 16 plus 16, so your simulation is, in a space of 16 cross 16 multiplied by 2.
Yeah.
And your observation is in a space 16 cross 16 multiplied by 1. So H will project from 16 cross 16 multiplied by 2 to a space which is 16 cross 16.
Yeah,
Because you are simulating only one component.
But you are resetting only one component.
Yes.
yes,
That's what it
and
is.
basically the other component is behaving like a kind of house-dimensional here, but the slave component is forced to also behave.
But you can use many components if you like.
Yeah.
But the covariance of the model is calculated only on the X or
Yes,
on
on the X. But
also the
you
covariance of the
can,
model.
but you can also do a covariance of all components. But then your covariance of matrix is becoming even bigger, and that could be a way of imposing on quantities which you can. So here we have the covariance matrix. Does this look
Diagonal?
diagonal? I don't think so. This is the covariance matrix of the 16 by 16 cube. And I don't really know what to make of this.
It looks strange because you are plotting it in 2D. Maybe you should be plotted in 4D. If you see what I mean.
No, what?
I mean, in your one direction
Yeah.
is basically your 2D taken as a 1D array.
I mean, you would not expect a block diagonal thing, of course, as we discussed.
But not here, right?
I know.
You see, your domain is like this, a 2D domain. But your one direction is that domain taken as a linear array.
Yes.
And then,
Here.
you see what I mean?
No. I mean,
So-
could you fix this by rearranging everything better?
Yeah.
If you put it
Yeah.
in 4D, yes.
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 I mean, I want, of course, to see something in 2D.
No, but you can.
No, but it's a covariance between 2D objects
Ah,
and
that's
2D
right.
objects.
Yeah, yeah,
That
yeah.
must be a 4D object.
Uh-huh. Okay.
So it will be kind of a block diagonal slimmed in 4D, which I can't of course imagine.
But
No,
the covariance
Yeah, right.
is only defined as between two one-dimensional.
Sure.
Yeah, but you can
Yeah, but-
arrange the element on your array, right?
But if
And
you make
reshape
it-
your matrix.
if you
you
make
can
it
do
one,
that.
visualize it.
You can do that to turn matrices that have band, for example.
Yeah, but the
Matrices
problem is, of
that
course-
concentrate the band in one position.
If you have a grid like this point is close to these 9 points.
Exactly.
But that's
And,
fine.
and this point is close to this point.
That's fine. That you will never give you a matrix like that.
No, it will.
Why? Because if you write the Poisson equation, okay? Poisson equation involves derivative operators that act on 9 points.
See, what he's doing is he's taking this as a one array, whole thing.
Yes.
Okay. So then the correlation between this and that becomes completely off. I think, see, there's a symmetric.
No, it doesn't. You get a band diagonal in the middle, and you get multiple bands on the side if you do that.
If you do what?
If you order your element properly, you get one band diagonal in the middle, and you get multiple bands
The
on
problem
the
is
side. But
here.
it's still a band in the matrix.
So, if you have this A, B, C, D, E, F, G, E, then this is typically A, B, C, and then you have a lot of this, and then you have D, E, T,
Yes.
and you have G, E, T, and these has to be,
Yeah, and you will get out of this basically 3 blocks, right?
And the distance is 16 or 32, what is the bit size? And it's not really a big distance.
I mean, I don't see how you can get a sparse matrix out of that,
He's not getting this part.
or a matrix which shaped like that.
Why not?
It should
because,
be banded.
It is one of the.
because every point here is
We want the
corresponding
band.
to
That's what the diagonal
every
line.
other point.
But no, but the point is that if you, they will still give you a band of the matrix.
Yeah, but they're
This is
shifted.
actually
Because you have bands which are shifted.
You have 3 bands. You have diagonal bands, And you will
Yeah,
have
but
an upper
you have-
band and a lower band.
Right, so this
You
will
have-
actually be an upper band. You see what I mean?
There's another
But,
thing
no,
that
but how many, you can have at most
Straight
9 bands you can have, okay? If you have 9 elements, you can have at most 9
So it
bands.
depends on how your correlation is.
See, if you're only really interested in your nearest neighbors, then you expect
It
big
depends on how your
bands.
correlation
So E is correlated with other 8 elements,
is. But
Okay. the 8 surrounding them.
You need to relate with 9 elements, itself.
you don't know how your correlation is falling off, right?
But you get more bands.
You get more bands,
Exactly.
but in that case, E will correlate with himself and with the 8 surrounding points.
and the limit is that.
And that you get 9 bands. You can't get any more than 9 bands.
And what you'll actually see.
No, whatever, no matter how many you have only 9 bands.
In fact, even less here, if you overcopulate.
Probably, yes.
Well, then you have 3 bands of 3.
3 bands of 3, yes, 9, that's why I say 9 bands, 9 triagonal things.
So, I got the eigenvalues of this thing, and this is the principal component analysis or something, and this says the biggest 4 eigenvalues correspond to 60%, 25%, 17, 10, and so forth. So basically, you should be able to describe this by 4 or 5 eigenvalues, and then it becomes much simpler. And then you, of course, can drop the lower eigenvalues, transform this thing back, and then you might get a nicer beast than this thing. So this basically has 4 primary eigenvalues, and those are the things we should look at.
Well,
That's
questions, other questions?
How do you try to use your knowledge in prediction of solar activity?
the problem. What model do you want to use?
No, in personal context is some model, yes, sure.
I mean, do you use, for example, a flux transfer dynamo, or do you use one with a Kirchhoff transport mechanism, or what do you use?
No, you should use your regular. Your
You're
regular
saying,
situation.
that's what I'm saying. What?
No, I mean,
If you
you're
don't
talking
really know.
about flux transfer model, you're talking about a model that runs on 11 years periods.
Oh, the transfer doesn't matter, yeah, but the dynamo model matters.
So to put
The
more.
dynamo matter.
Actually, you do in some sense, in a simple way, it was how to say realized this program by Alexander Sojin. But in very simple model, maybe to use more complicated spherical model for solar activity with toroidal field. Somehow to put model which produced a Wolf number in toroidal field,
Yeah.
something that is spirit.
So,
That is, of course, he knows the field by Kirchhoff.
But it's not, it's another problem, because
Well, it's that problem, essentially.
it has really made in plane geometry. Plane, I think it was not spherical.
No,
It was a 1D spherical model.
No, but in that one, it doesn't really matter, because they're just comparing the sunspot number with the magnetic field. It's extremely crude.
Yeah.
so there is this is of course related to the solar cycle predictions of the Putty and et al. That in a way that's exactly what I did here. Take and set the value of the observation, set the parameter, set the variable in the model to the value of the observation.
That's not clear.
And according to this, it kind of works. But in the real case, I'm
But
not
I
so
think even the hypothesis is not clear exactly which variable of the simulation is being set to which variable nowadays.
and how.
How is the next question, but which are the corresponding variables? In the simulation, you have the magnetic field.
Yeah.
In the observation, you don't have the magnetic field over the whole domain.
Yes.
So I think they were just taking the sunspot number.
Yes, and that is of course a problem because you have the H matrix, and the H matrix for transforming from smaller spot numbers to B fields.
Or opposite. Opposite. Before observation, what number in some sense?
Because you have them both ways, because you invert the damping.
So wait, so the H must be inverted?
No, because you usually can't, and then you have to cheat and do great separations.
Which actually is not important.
Basically,
It's not, but the question is in that procedure, do you need to be?
should be done in 1 year's time, and then I'm taking on this problem using another set of students.
Okay, first of all, we need to choose what model of dynamo we should use as true. But honestly, I think toroidal and colloidal fields with some model of what numbers function of one field, not so bad.
And then you need some mechanism to form some spots.
We don't know precisely what the
Yes,
meaning
but
is,
you
but at
see-
least what we understand is some kind of concentration of magnetic fields. No, I believe that. I think either.
Other people-
Some measure of the number of sunspots or the magnetic field or something. For example, in our prediction we counted the number of eruptions, whereas motion counted the motion predicts the amplitude of the square or something.
Begin the first problem is there is no correspondence between something you have, I mean your code doesn't have eruptions, for example. Right? So the correspondence is arbitrary. Motionless code doesn't have some spots, so to say. So the correspondence is completely arbitrary between the code and the measurement.
Yes. Yeah, I mean, it's not the real science.
So logical is in the model sense because the model doesn't have the property.
And then you have this problem once again of finding the true state, especially if you have a H matrix which is dubious.
Let me ask you some technical question.
Yes.
How is your algorithm different from ensemble Kalman filtering?
So Kalman filter, first of all, doesn't use the R and B matrix explicitly. They are basically using the same basic statistics machinery, but calculate the error statistic explicitly as it goes on. So that is the difference of 3D bars. Here this is a B matrix. In Kalman filter, they are counting the errors.
So in some sense, they will be running many copies of the same system and keeping calculating the error. within
Or
it.
something like that. And then you do an ensemble simulation of it to basically say we are not interested in a single realization like this one or this one, or we are rather looking at a bundle
Yes.
of simulations. And then you have a extended ensemble Kalman filter, which does some features with the thing that linearly interpolate the non-linearities. Because the 3D bar assumes that you have a Gaussian noise, and then it assumes that basically the system is linear. And the more non-linear you get, the more minimums you get. It's very hard to find the global minimum instead of a minimum. And Kalman filter has basically the same core problem that it's fundamentally a linear thing that really has issues when it comes to the non-linear road. But they're basically the same family of things which is taking a different road, and then it is the ensemble thing, which is what here. We're gonna shoot you.
The only advantage of the ensemble is it's not assuming anything about the error, but just calculating it itself at the cost of running many copies of it.
It could be that actually a single realization might not give us as much information as an ensemble of them, and look at the distribution. But basically what other people are doing, they are having simulation, and then they say it is raining in one of them, and it's sunny and nice in 90% of them, and then you can kind of say it's 90% chance that it's going to be sunny.
Multiple universes. So in one of those universes there is a nice director.
So basically
Well, linear is universe.
so basically the plan is to have the machinery in the pencil code, and then you can basically replace this with whatever you are running and compare it with whatever you are running. And now it's a very crude thing, but it seems to serve the purpose. But there's of course still a lot of job to be done.
Can one interpret the corrections that the machinery is doing in terms of now almost physics? I mean, in this following sense, if you think, for example, of magnetic fields, and you observed magnetic fields, and you want, of course, the simulations to reproduce that, how would the simulations do that? Would they essentially do this by putting in an electromotive force or a source function which is perhaps even aligned with the mean magnetic field, or something like this? Could that be a possible outcome of such a correction?
I don't know. I think the best how this is kind of set up is you are kicking it.
When what?
You are just impulsing.
Yes.
And that is of course the problem with the 3D bar, that you have these jump things. And if you want a really nice thing, you do a 4D bar, and then you basically start and you just change the start point and basically say 4D bar, basically run the green one and say, oh, the green one wasn't so nice, let's run the black one. And then you have a full, really physically nice thing with no spikes and jumps and so forth. And that is the advantage of the 41.
Your model, the model that you are resetting or whatever, it must be able to handle properly the noise that you are introducing when you reset to the observation. For example, if I have a magnetic field, okay,
Yeah.
and I say I want to reset to the magnetic field, and I do a measure of the magnetic field with an error, that magnetic field plus error will not be solenoidal. There's no chance of it. But I cannot take a non-solenoidal field.
If you did this in terms of A, it would
Yeah,
be.
but you don't measure A, you measure B, let's say. Let's say you have B as a measure. And you want to plug that there. You cannot do that, right? Because your system, I mean, your system
But your error in the measurement of magnetic field
will make it non-solenoid.
may make it non-solenoid.
If you plug into your equation, what will happen to your model?
Possibly you will kind of have two parallel evolution, one of the solenoid part and one of the part.
But I mean, in this case, it's adding the velocity. If you have, for example, a compressible flow, but you add noise, but you have a compressible model, sound wave will take care of dissipating that
So
noise.
that's exactly what Axiom said, yes.
But the question is, if in that case you will do this, but for the magnetic field you will need a code that can handle magnetic monopole, that can dissipate that somehow, right?
So magnetic monopole can be completely independent without particular
I mean, right, you
But
just
you
impose
don't-
noise, so you can add the noise in terms of a curve.
And it depends on the code. If you have a spectral code where the
No, but you have observation.
when the expanding system is pointing to another entity, then by projecting the initial condition to these nodes, the zero will immediately be wiped out. They no longer exist. Because they have a projection.
Yes, but in that case,
Yes.
it will not be.
Okay.
It will not be the physics who takes the physics of the systems who takes care of your deviation from the attractor. It will be your model that your numerics that takes care of the deviation from the attractor. So my question is, does the numeric takes care of the deviation from the attractor in the same way as physics does?
Right.
Or maybe the numerics will just jump you on different attractors,
Yeah.
while the physics will jump you on the correct.
So true. And then we have a program on this. Yes. So let me remind all of you that, of course, Nordita is running a program on exactly this topic of data assimilation that will be throughout the month of May next year. And then that's it. And now there's this little teleconference with Petri, which is starting in 2 minutes. So.
Could someone tell something? How do I turn this monster off?
What do you mean?
How do I turn this?
You mean change back?
Yes.
I don't know.